Welcome to Theory Lunch, everybody. Today we're going to have Roie Levin talk to us about fully dynamic submodular cover with bounded resource. So welcome, Roie. Take it away.
Thanks, Isaac. Hello, everybody. Thank you all for coming. Thank you especially to my committee for agreeing to be here. Today I'll tell you about fully dynamic submodular cover with bounded recourse. This is joint work with Anupam Gupta. So, let's jump right in. Before I start, if any of you attended a talk I gave about a year ago, you might have some mild deja vu from the first part of my slides, but I promise it's indeed a different talk, so just bear with. So let's jump into a motivating problem. You're given a graph and a set of clients in this graph, and each client wants to route some demand worth of flow to a server, and our task is to place the smallest number of servers in this network such that every client can feasibly route its flow to some server while respecting edge capacities of the network. Now, furthermore, there's some operation cost to running these servers, so we want to minimize the number of servers we have open. Okay, and this is the task. But really the task is harder because we don't know anything up front, and instead we're only revealed the clients one by one. And in fact, the clients are going to come and go over time. And as they come and go, we'd like to maintain sort of a near optimal choice of servers. And on top of this, we don't really want our choice of servers to move too much. So maybe there's a setup and a teardown cost to the servers, and we want to avoid sort of changing our solution too much from time step to time step. So maybe this vertex comes in, this client comes in, we decide to place this server, and it can route this way. A second client comes in, we place this server, it decides to route this way. A third client comes in, maybe it can reuse the second server. And now the second client disappears, and we decide, well, this is a feasible solution. Everyone can route their flow, but maybe we'd prefer to save on server costs and actually open a new server here and route them both this way. So our goal here is to always maintain, as I said, a near minimal number of servers in the network, and to also minimize the number of servers we buy and sell between time steps. And this notion of how many servers we buy and sell between time steps is commonly referred to as recourse. This is sort of the number of takebacks in our solution. Sometimes people talk about this in the language of consistent algorithms, but I'll use this terminology for the talk. By the way, does someone have their mic on? I'm getting some feedback, if you or some background noise. Thank you. Okay. So how do we solve this complicated combinatorial problem? Well, it's helpful to zoom out and try to abstract the core features of this problem. So what do we have? We have n choices of possible servers. These are the vertices in the graph. And we'll denote this by this cursive n. A solution consists of a subset of those choices. There is a cost associated with any one solution. Okay, so if we pick some set of servers to be our solution, the cost is just the number of servers in the example I gave. There's a notion of coverage quality, right? This is the number of clients covered when you choose S to be the candidate set of servers. And I'll just foreshadow that sort of the way, in the problem that we're trying to model, this notion of coverage itself is evolving dynamically. And I'll say more about what this is later. But for now, this is our sort of optimization problem. In its abstract form, we're minimizing over choice of subsets of the ground set n, the cost of that subset, subject to the constraint that the coverage of that set is maximized, i.e., in the server example, we've covered all of the clients. Every client can feasibly route its flow to some server while respecting edge capacities. Now, if this is all I told you, this problem is fairly hopeless because, I can make arbitrarily sort of hard to optimize functions f, and you'll never be able to solve this efficiently. But thankfully, we can assume a few more things. So for one, the function f that we have is monotone, meaning if I have two subsets, A and B of the ground set, where A is contained in B, then the coverage of B is always better than the coverage of A. More servers is always better. Okay, so if that's the case, then we can rewrite our optimization problem as f of s equals f of n, just because every monotone function is always maximized, when you take the entire ground set. F is non-negative. That's fairly self-explanatory. And furthermore, this function f is what's called submodular, i.e. it has a decreasing marginal returns property. And I'll say a little bit more what this means. So a function f is said to be submodular if for any two subsets of the ground set A and B and any x outside of both A and B, we have that f of A union x minus f of A is bigger than f of B union x minus f of B. And what this means is that the sort of benefit of x to the set A is better than the benefit of x to the set B. Okay? If I introduce this notation of conditioning, I'll say f of s condition on t is exactly sort of the marginal value of s to t, f of s union t minus f of t. Then we can rewrite the definition of submodularity very cleanly, just like this. Just to kind of ground this concretely, you know, my valuation function for cars is said to be submodular. If buying a fancy car gives me more value if I don't already have a fancy car. Make sense? Any questions thus far?
Yeah,
Okay.
I have questions. So that the way this notation is just says that, right, the marginal improvement by adding x to A is this funny notation fx bar A.
Exactly. So
Okay,
I'm literally
okay,
just rewriting
sure.
this thing.
Okay,
It'll just
sure.
be sort of like visually appealing to write it this way.
Can I ask you something about the previous part of the setup,
Sure.
the setup of the system?
Mhm.
Is this an example of a metrical task system? So
Okay, yeah.
do you know what a metrical task system is?
Yeah. So remind me exactly sort of the general version. There's a metric and you serve like a request. You have to move there and then pay the sort of service request, right?
Right. There's some to satisfy. There's a sequence of online requests occur, and then you have to move to a state that satisfies the request.
Right.
And you pay for the change of your state. Like in this case, the state would be the set of server locations, the subset of servers, right, where they are.
So the only,
And
so
then
one immediate difficulty is usually, I think that's K fixed servers, right? And here we're allowing for like a change to the number of servers. So already if you want to model it that way, you'd have to do something funky with like.
I don't think so.
Am I wrong?
The state can be any set of states, which would be like one state would be having one server, another state would be having all arrangements of two servers,
Okay, that's
all
yeah.
arrangements of three servers, and so
That's
on.
what I'm saying. Yeah.
So the state could be. I'm not saying I know the answer to this question. I'm just because I remember way back in the in the 90s we were working on these kinds of problems, and we set up these things called metrical task systems. And there were some results, general results on solving them. But I'm just trying to understand if this is different from that.
Yeah, so
or if
let me.
this fits into that framework or not.
I should know the answer to this problem. I think it's easy to resolve, but let me just take it offline because I don't know off the top of my head. So sorry.
Okay.
Yeah, but I will answer this maybe at the end of the talk. Yeah, that's a good point to make.
So yeah, maybe a quick comment to maybe in the metrical task system, the costs are soft in the sense that you can have fewer servers, but then the serving cost will be more, and then you just add up the cost of the servers and the serving costs. Whereas here you have like a hard constraint that f of s must be f of n. So that's like you have to serve all clients possibly within some distance, right? So this sounds like in that sense maybe a harder problem because you have a hard constraint to meet. But I could, yeah, I'm just guessing.
But I thought the metrical task system framework was you have the state and you have the request. And there's a cost of a request in that state. And it seems like that would cover all these structural properties that you're talking about. Like if you define it so that if the state doesn't cover, is not close enough to the server, then it's not allowed. It doesn't satisfy the request. I don't know. Anyway, I don't want to derail the talk with.
Yeah, let's. No, it's a good point, Danny. Let's maybe resolve it offline. Yeah.
Okay.
Thank
fine.
you. Okay. Okay. So all right. So this is our problem. We're solving the min cost subset selection problem. subject to this constraint that f of s is equal to f of the ground set. And the function f is monotone, non-negative, and submodular, and evolving, whatever that means. And I still haven't said what that means. And what we want is we want a competitive solution at every point in time, even as this function is changing. And we want low recourse. All right, so we want our edits to the solution to be sort of small. And we're going to basically solve this fully general problem, and we'll get the server problem as a corollary for free. Right, so this is our goal, and we're going to do this in this talk. And for this talk, we're just going to assume that f is integer valued for simplicity, and that all the costs are 1. But in the paper, we handle the general case. So what is this problem? Well, offline, it's called the submodular cover problem. It was introduced by Woolsey in 1982. And what Woolsey showed is that the simple greedy algorithm that just repeatedly sort of selects the element of largest remaining marginal value, then this algorithm produces a solution that's within a multiplicative log of f max plus 1 of the optimal solution, where f max is the maximum over all the elements in the ground set of the singleton value of that, the value of that thing as a singleton. And furthermore, this is known to be the best you can possibly do unless p is equal to np. So already this gives a log d approximation for the offline version of the server placement problem that I talked about, where d is the kind of the total demand in the system. And this problem is known as the simultaneous source location problem. It was introduced by this team, Andrew, Garrett, Golovin, Maggs, and Meyerson. Okay, so let me try to convince you that this submodular cover problem is very, very expressive. So for one, version 0 of this problem is known as hypergraph vertex cover, also known as set cover, also known as the hitting set problem. But we'll stick with vertex cover terminology just because it'll make things less confusing. So in this problem, we're given a collection of hyper edges. These are just subsets of a ground set. And we'd like to pick the smallest number of vertices such that every edge has at least one vertex hitting it. Now, why is this submodular cover? Well, we can define our submodular function to be, it's a function of subsets of vertices of the ground set, and we just let it be the number of edges that we've hit when we choose that subset of vertices. This is called a coverage function, and one can show that this is submodular. Now, if you know something about approximation algorithms for hypergraph vertex cover, you may have heard that the greedy algorithm gives a log n approximation, where n is the number of these edges, and that this is the best you can possibly do. And indeed, f max, which recall is the max number of edges that any one vertex can cover, is at most the number of edges. And so Woolsey's algorithm and analysis generalize the log n guarantee for set cover. But submodular cover goes far beyond vertex cover. So here's a simple example that's not clearly a case of vertex cover. What if I say, same story as before, we have these hyper edges and we'd like to cover them, but I don't need you to cover all the edges. I'm okay with you stopping at some threshold tau. This is not in any obvious way an instance of vertex cover, but if you define f to be the min of the same coverage function and the threshold tau, meaning you're fully feasible if either you've covered all the edges or you've at least passed the threshold tau, well, this function f is still submodular, and so you can still use the greedy algorithm. Okay, and you can kind of go crazy. You can define a capacitated variant of this problem. You can Frankenstein these two together, and so on and so forth. So beyond theory applications, I want to stress that this problem is really used in practice in a lot of different areas. In robotics and sensor placement, if you want to place sensors to measure uncertainty about the world, this is often modeled as a modular cover. Viral marketing and social networks, if I want to pick influencers to maximize influence. In machine learning, if I want to pick a small set of features or keywords to summarize a document, these are often modeled as modular cover tasks. And it's really become quite a popular paper template to take your problem and reduce it to submodular cover and use the greedy algorithm as a black box. So here's kind of a laundry list of papers that do this. And I guess my point here is that if you work on submodular cover, there's a good chance that it has some downstream ramifications for other work. And actually, like a lot of these are like kind of perfect for dynamic settings and make a lot of sense to study in the dynamic setting. So in particular, this paper by Lukowski, Rost, and Schmidt stresses the importance of not changing one's solution too much, although they sort of don't give algorithms that work in the dynamic setting. Any questions?
Could you say what the greedy algorithm is again?
Oh, sure. I'll actually say it more specifically in a little bit. It'll sort of be a cornerstone of the talk. So we'll, yeah. But I can, yeah. Would you rather I go back or I can just get to it later?
No, you can go ahead.
Okay. So in what remains of my talk, I'll do the following. First, I'll tell you sort of more explicitly what the fully dynamic model really is. Then I will state our results. I'll describe the algorithm. I will hopefully give you the entire analysis, although it will be just for the unit cost case. And then I'll discuss some other results we have in the paper and conclude. Oh. Okay, let's get to it. So in our model, we want to model constraints arriving and leaving over time. And so we're going to imagine that we are holding on to an active set of submodular functions. And this is this capital G. And the little g is a submodular function. So at time 1, maybe we have this one submodular function. At time 2, we get another one. Time 3, we get another, and so on and so forth. Maybe at time 5, the third submodular function is deleted. And what we'll do is we'll define ft to be the sum of all the functions currently in the active set at time t. And at time t, we want a solution st for this function ft, i.e. a set s such that f of s is equal to f of n. This is the submodular constraint from before. And you'll notice that because f is just the sum of these independent functions, f is maximized if and only if each of its constituent functions is maximized. So really what we're forcing here is that a feasible solution be a feasible solution for the and of all of these constraints. All right, and our goal—
Could you say that again? Well, why is it optimized when each individual one is optimized?
Just
That's
because they're
normally, okay, go ahead.
They're independent functions. And they're monotone submodular functions. Oh, crucially, they're monotone, sorry. In our problem, they were, yeah.
Okay, they're monotone
can you give an
functions of a, sorry.
Oh, I was just asking, can you give an example of these functions?
Absolutely, I'm gonna do that in on this slide, yeah.
Oh, okay, but I still don't understand more basically, like, well, you're passing some arguments into those functions. Isn't that the set of sites or something that are being considered at time t?
That's right.
What are you passing? But then they're all you're passing the same set of thing into all the functions. They're not independent anymore.
That's right, but they're all monotone, so you only do better by yeah.
By doing, by adding.
By adding stuff, yeah.
Adding stuff.
Yeah. So it'll be clear sort of in the example in a moment.
Okay.
I hope. And if not, ask me again, yeah. Okay, so we want to maintain a feasible solution. We also want to keep recourse low. And by this, formally, I guess I mean the sum over time of the symmetric difference, the size of the symmetric difference of our solutions at successive time steps. So every time we add something to the solution or get rid of something, we pay 1. But we'll do this trick where actually we'll only count the insertions. We'll count the deletes as free. And the reason we can do this is we're summing over all time. And so we can just say, okay, when you enter the solution, you just pay 2 upfront and you'll prepay for your delete. And then the delete will be free. We'll overcount by at most a factor of 2. Okay, so let me do an example and please ask me if it doesn't make sense after this example. So let's do the hypergraph vertex cover example in this sort of, in this framework. So in this setting, each of these constraints, which is a submodular function, is just the indicator function for whether or not the ith edge is covered. So the first edge arrives, and our active constraint set is just the indicator for whether this first edge has been covered. Okay, we pick a vertex, and we're maximizing this this G1 and also the function f. A second constraint arrives. It's the indicator function for the the first two edges. So, you know, we've maximized F and G with the same choice, and our two G1 and G2. A third edge arrives. Now our F value is at 2, but it should be at 3. So we add this vertex, and so on. A fourth edge arrives. Maybe we need to pick this vertex. Maybe the third edge leaves. And now we're feasible, right? So the value of our function F is 3, and it should be 3. But we're overpaying, and we might decide that, you know, for the purpose of keeping a small solution, we might want to pay the recourse and get rid of this.
Could you go back one step in that simulation?
Sure.
Okay. Yeah. That's suboptimal. You have 3 stars when you only need 2.
Absolutely. That's why I'm going to get rid of the star. And so, like, I guess the point here that I'm trying to demonstrate is that there's a trade-off between maintaining a near optimal solution, but also maintaining sort of a stable solution that doesn't oscillate too much. And these things are in tension with one another. It's hard to do both. Now, we can't really get the optimal solution. I mean, even offline, we can't efficiently solve this problem. So we'll settle for like a near optimal solution. And I'll say sort of more specifically what the trade-off we achieve is in our results. Does that make sense? Did I answer the questions?
Yeah.
Okay.
Yeah.
Thank you. So let's say the results. So here's our main theorem. We show that there is a polytime and furthermore a deterministic algorithm for this fully dynamic version of the submodular cover problem that achieves 2 things. One is it always maintains a competitive ratio that's order log F max. And recall, log F max is the optimal thing that we can achieve even offline. And so this is within a constant factor of the best we could possibly do. And when I say, by the way, when I say beta competitive, I just mean cost within multiplicative beta of the optimal solution. And the second thing is we show this average recourse bound. Okay, and if this is sort of a lot to take in visually, we'll unpack it slowly, hopefully. It's the average over time of these GTs, which recall were the constituent submodular functions, evaluated at the entire ground set, times this extra logarithmic term. And inside the log, there's a ratio of costs, Cmax and Cmin, and these are just the maximum and minimum element costs in the problem setting. So let me, just to clean this up, sort of get rid of the log term and use this O tilde notation to ignore it. And up to the tilde, I claim that this bound is really sort of the optimal, or it's the best you could possibly hope for in general. So why is this? Well, in the case of the hypergraph vertex cover, recall each of these GTs, these constituent functions, were indicator functions. They were saying, you know, is the ith edge covered or not? And so this sum over time is just at most, is at most big T, the total time. And when we're averaging over time, this just gives 1. And so this is giving a constant up to the log factor, a constant recourse bound for dynamic hypergraph vertex cover. And you really can't do any better than this. So if I did the same, if we played the dynamic hypergraph vertex cover game, and every time I gave you a subset that was completely disjoint from the previous subset, you'd have to buy a new vertex every time to cover it. So you can't get away with less in general. Does this make sense? And by the way, this gives us a corollary, an answer, and also like up to the log factor, an optimal answer for the dynamic version of the source location problem, which is the server problem that we talked about before.
Can you explain what F max is again? I forgot the notation.
Oh, sorry. Yeah. So F max is just the max over all. Oh, I have enough to go 2 back. Yeah, it's the max over all elements V of F of V. So think of it as just the biggest like single marginal value that I can get. Does that make sense? So in vertex cover, this is like the number of edges that any single vertex can cover. It's like the biggest benefit I can get from choosing any one element by itself.
So it's the degree of the graph, the hypergraph?
Yeah, in this problem, it's exactly the degree. But more generally, sort of for submodular cover, it's like the biggest benefit I get from any one element. Does that make sense?
Yes,
I don't think it's going to be too important, but I'm happy to clarify again. Yeah. Okay. So that was that. And in our paper,
hold on, sorry, I have another question. So the competitive ratio is when you are comparing which two quantities again?
Oh, good. So we're comparing like at time t, our standard, our goalpost is like the optimal solution at time t. So it's really like a very stringent guarantee. We're saying, suppose we're solving the offline problem at time t, we want to get the optimal solution at time t. And we want this for every time t. So, sorry, we're comparing like the cost of our solution with the cost of the optimum.
I see.
Normally, competitiveness is in terms of a sequence. You accumulate the cost of everything up to that point. Is that
right? No. So this is even stricter, I guess. Like,
I think this is slightly weaker, right? Because you're like, I think the normal competitive ratio would be if you're not allowed to, you have no bounded recourse, you can't change at all. Right. This is letting you change a little bit, which you know, gives you more power, but also like you're asking for stronger things. Yeah, that's exactly right. We'll actually like compare this with like more classical online results in a moment. Right. Quick question. So this algorithm is deterministic. So the average, it's really the average recourse deterministically. But do you have like, is there like a bound on the worst case per time step recourse? No, that's one of my open questions at the end. Okay. I won't but the techniques we use are fundamentally kind of amortized. Got it. Thanks. So in our paper, we show this other theorem, which is an improved bound for a special class of functions. So we do solve the general submodular cover problem, but if you assume that these functions are additionally so-called 3 increasing, and I haven't said what this is, then we can essentially achieve like a logarithmic competitive ratio again, and achieve the truly optimal recourse. So we show how to get rid of the annoying log factor for this special class of functions. Now we trade off, like this is a slightly worse term inside the log, but it might not be a huge deal depending on your setting. I guess I'll leave describing this class until the end of the talk. If I have time, I'll get into it. But the main thing to know is that this class also includes hypergraph vertex cover. And so this theorem gives us a truly O of 1 recourse bound for the dynamic version of hypergraph vertex cover. Okay, so let's just relate this work to previous work. So Anupam with some co-authors gave the first log n competitive and order 1 recourse algorithm for the special case of hypergraph vertex cover in 2017. And you might wonder, like, well, could you just adapt their techniques for this more general problem? And really you can't. So their paper cleverly maintains an assignment of the edges. These are those ellipses, 2 vertices that are covering them. And although this approach is very clever, it really fails in the setting of submodular cover because there's no more edges to track. There's just this kind of nebulous notion of coverage and maximizing this coverage value, and it's not completely clear how to map this to that. So one angle on our work is that it's simplifying the analysis from their paper and simultaneously generalizing it to a much broader class of coverage problems. And the second thing is earlier this year, Anupam and I had this paper where we essentially solved the online variant of this submodular cover problem, which is maybe relating to the questions you asked me, where no takebacks are allowed. And there we show the optimal possible competitive ratio of log n times log t times f max. It doesn't really matter that we understand this bound. But this is the competitive ratio in this like summed sense over time because we're not allowed to take back our decisions. But this really fails in our setting, and it's kind of like very fundamentally an insertion only version. Like you can't maintain a solution with no takebacks when there's insertions and deletions of the constraints. And so another way to view our work is that we are showing that with this like minimal possible like recourse, we're allowing ourselves just the minimal possible amount of recourse, we can both remove the extra log here. So we'll get down to a single log of F max. And we can extend this framework to this fully dynamic insertion and deletion setting. Any questions?
I had a question. So, you know, this like log and the competitive ratio is kind of necessary when your coverage functions are like, you strictly have to, you know, maximize your submodular covering function or like vertex cover everything.
Mm-hmm.
Have you thought about like, if instead I only have to like approximately cover everything, so my problem looks less like set cover and more like max coverage or something, then can you get constant competitive ratio and still low recourse?
So you're asking about a bi-criteria version of this, where like you're allowed to?
I mean, it could be by criteria, or you could just define the like coverage as like, you know, cover within 1 minus 1, or like all but a small fraction of everything.
So that's an instance of partial cover, which is also an instance of submodular cover. So you can actually, for free, model that in this framework.
Yeah, I guess my question though is, does that buy you anything? Does the problem become easier if you know sort of like the coverage you're shooting for is bounded away from the maximum value of your coverage function?
Oh, that I don't know if the problem is still hard. I mean, in general, the partial cover problem is just as hard because you can set your threshold to be everything. But off the top of my head, I don't know if the problem gets easier. Oh, well, there's this yeah, I'm not totally sure. Is the short answer.
Okay, thanks.
Yeah. But there's a lot of ways in which you could sort of change this framework and find interesting problems. All right, so let me get to the algorithm. So this is the greedy algorithm. Danny, I think you asked about this, so here it is. So suppose I threw this problem at you, this goal of ours. One thing you might think to do, which is not a great idea, is to just run the greedy algorithm from scratch every time. So every time my world changes, I get a new constraint or a constraint leaves. I just throw out my old solution and run the greedy algorithm from scratch. So here's what the greedy algorithm does. For n rounds, where n is the size of the ground set that I'm considering, I'm going to condition on the elements I've taken so far, E1 to EI minus 1, and then just pick the element that gets me largest marginal coverage. And I add this element to my solution and I repeat. So the greedy algorithm might look like this. At time t, I have some function that I'm trying to maximize, ft. And this is the kind of stack trace of my greedy algorithm. So first it picks the yellow, then it picks the purple, and so on and so forth. Now, because it's always picking the element of like largest marginal value, we get this monotonically decreasing histogram. And then at some point, all the elements remaining have like 0 marginal coverage. They're no more value to me because I've finished maximizing the function. And so we'll just draw this vertical line to denote the stuff that we don't take. So our solution is kind of the prefix here that has non-zero height. Now, what's the issue with this? Well, at time t plus 1, the world changes completely. Some coverages, sometimes coverages might go up, sometimes they might go down. We've run the greedy algorithm for the wrong function. And so we shouldn't expect our histogram to look correct. So the new greedy, it drank too much caffeine and it just says, whoa, 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 put this here, put this here. You need to completely reshuffle your solution if you want it to be the right greedy algorithm. And if you're doing this, you'll come along and you'll throw out your old solution and just, buy this new solution. And this might cost a lot of recourse. So this is not a good idea, but here's a better idea. Instead of like fully accepting the greedy solution, we're just going to walk slowly towards the greedy solution and stop at a point that's sufficiently competitive. And we don't need to fully reproduce the greedy's algorithm. We just need to get close, or it suffices to get close. Okay, so our algorithm is going to maintain a permutation pi on the elements of the ground set. just like the greedy algorithm. And we're going to think of this as the stack trace of some auxiliary algorithm. And our solution will sort of be induced by the permutation. It's just the prefix that has non-zero height. So our goal is to get this stack trace to look like the stack trace of a greedy algorithm. We're going to track the coverage vector, okay? And I'm using this word just to mean the vector where every coordinate is the height in this diagram. It's just the marginal coverage of each element. So it's just this sort of the vector in this represented in this histogram.
Roie,
oh, please, yeah.
I understand something here. So is this vector so first I choose the best one, then given I've chosen that one, I choose the next one. Given
Exactly.
I've chosen that, etc.
Yes.
Okay. So it's like it's not what would each of their value be at the first moment in time.
Absolutely. It's very order dependent. And this will hopefully be clear in a moment. Yeah. So we're going to run some kind of local search on this permutation. And I need to argue to you two things. One is that this local search terminates at a competitive point. And the second thing is that we don't need to perform too many local search steps before it stops. So here are the two kinds of moves that we consider. One is a swap. So if we have 2 points in this permutation, if the text is confusing, just look at the picture. We have a position, I and a position I plus 1, the blue and the red, such that the blue is shorter than the red. The marginal value of I is smaller than the marginal value of I plus 1. Then we'll swap them. So this is like a bubble, as in bubble sort. Now already this feels like it should kind of move us towards the greedy solution, because if we keep doing this, we should get to like a monotonically decreasing solution. But we'll need one more kind of local move, and this is called a gamma move. And this is kind of the most interesting part of this algorithm. A gamma move is the following. We move an element u from position q to p if for any index I in between p and q, we have that the marginal value of u given the prefix up to p minus 1 is bigger than gamma times the marginal value of I given the prefix up to I minus 1. So that's probably a lot to take in. So the picture makes this clearest. The black element moving in front of the red element is a legal gamma move if the height of the black element after the move is much better, i.e. gamma times better than the heights of anyone it cuts in line before the move. So when black cuts ahead, it's going to potentially steal some amount of coverage, some chunk from each of the coverages of these other elements. And it will potentially get taller. And we're allowed to make such a move if it gets like way taller than any of these people. Now you'll notice, so in swaps, when red cuts ahead of blue, red might get taller and blue might get shorter, but never the other way around. So red will never get shorter and blue will never get taller after this move. And the reason for this is exactly submodularity. So when red moves ahead, it's conditioning on fewer things. And so its marginal value can only increase. And likewise, blue is conditioning on 3 things instead of 2 now. And so its height can only decrease. Similarly, sort of with these gamma moves, like black can only steal mass. It'll never give mass to any of these people. Okay, so one thing to note is that swaps always cost 0 recourse. When you do a swap, you're never swapping things with non-zero value. And so you're never actually adding anything to your solution. You're just sort of doing this exercise in your head. On the other hand, gamma moves might cost recourse, namely if the element moving comes from the tail of the permutation that has no coverage. Any questions about this? Okay.
Sorry, I do have a question. When you're talking about this recourse, you're saying, if I did this swap and then stopped and said, okay, now I will give the solution implied by take everything with non-zero cost in this vector, non-zero value in this vector. Okay, got it.
Yeah.
So that's what you mean by recourse is if I do this search and then take that solution.
That's true, but actually our bound will even like, if we imagine paying even for the intermediate solutions that we don't actually present, really we're running this algorithm and we only need to present the solution after we've terminated the local search. But actually we can even pay, every time we add to this intermediate solution, our bound will also apply to that.
Okay, got it.
It should make sense in a moment, yeah. Okay, so let's jump into the analysis. So the competitive ratio is actually very easy once we've set up this machinery. And let me convince you of this. So suppose for the sake of contradiction, we have a situation where an element, so we've picked two elements, 1 and 2, and now some element, the third element, let's say, is less than gamma times the best possible element I could have put in this place. I.e., there's some blue element such that if I put the blue element instead of the red, it would be gamma times bigger than the red's current height. Okay? Well, we assume the solution was stable. And what stability means is that there are no swaps for 1. Okay, and if there are no swaps, the solution is sorted in monotonically decreasing order. So not only is blue gamma times better than red, but blue is also gamma times better than everyone in between, because all these people in between have to be shorter than red. And so such a move, moving blue ahead of red, would be a valid gamma move. This is the definition of a gamma move, right? Blue moving ahead of red would make blue's height gamma times bigger than anyone in between. And so the point here is that at a stable solution, i.e. a solution where there are no more moves available, we can't have this situation. So meaning red must be within gamma of the best possible element, i.e. that the element of like maximum marginal coverage from this point on. And so on termination, pi must be the stack trace of an approximate greedy algorithm. It's kind of, fudging the greedy algorithm up to a gamma factor. What you can do is now go back into the analysis of the greedy algorithm, and you'll notice that the fact that you're not running an exact greedy algorithm, but just this gamma approximate greedy algorithm only adds an extra gamma factor to the competitive ratio.
And should I think of gamma as a constant? Because earlier you said the competitive ratio is like log of F max.
Good point, yeah, absolutely. So gamma is going to be a constant. Yes, that's a very good point. We'd be worried if it was not. Yeah, so gamma we're going to fix once and for all. Like we'll wait till the end of the analysis, but it's just a constant in your head. Okay, so that's it for the competitive ratio. And all I need to do now is convince you that the recourse is not too big. And this is really sort of the crux of the paper. This is the most interesting part. The way we'll do this is we'll use the potential function method. So we'll write some potential function that is a function of the permutation that we're maintaining. And we'll think of this as some kind of like energy that's remaining in the system. And we'll show a few things. One, that this thing is non-zero. Actually, this should be greater than or equal to 0, sorry. It doesn't really matter. This potential never increases with swaps. So recall we said that swaps never cost recourse. And so if we can, we're just going to make sure that swaps never, accidentally add energy to the system. And then we'll be able to sort of do swaps for free. We're going to argue that this potential increases by at most some amount when a constraint arrives or leaves. So when something happens to the world, the energy in the system increases by some bounded amount. And then every time we perform a gamma move, we're paying one recourse, but we're also spending some energy from the system. And we're going to say that this phi decreases by at least something. So let's fill these in. Here's the function we're going to use. It's just the sum over the indices of this coverage vector of some concave function of the coverage vector. So recall this histogram that we drew. It's just a concave function of like each of the entries in the histogram. And specifically, we'll use this concave function, x log 1 over x. The specific number we get is this one. Well, for the increase per time step. And then with every move, every time we pay recourse, we spend at least one amount of energy. And this will give us the following bound. Okay, we just divide this number by this number and sum over time. And this is our total recourse bound. If we want the average recourse bound, we would just divide this by t. And of course, like you might notice that this quantity is nothing but the Shannon entropy of this coverage vector. So as a philosophical aside, like this both kind of makes sense and is somewhat interesting. So, roughly, if we're trying to minimize the unit cost cost function, we're trying to find a solution of small support. And really, this should kind of correspond to low entropy, roughly. And so, every time we do a gamma move, we're kind of playing cleanup. We have our mess strewn out across the floor, and we're kind of like scooping it up and putting it into fewer and fewer buckets. And it kind of makes sense that we're reducing entropy in the system. On the other hand, it's also interesting that we're reducing entropy. So oftentimes, algorithms operate along this max entropy principle where they try to maximize entropy. And here, like very crucially, entropy is decreasing. So it's somewhat interesting. Now, you might be wincing a little bit because this number is not exactly what I showed you earlier. And you might wonder, like, can we do better? Like, am I misleading you here? And really, I presented this in this order because this is the order in which we came up with this. But then we realized that actually you can replace this entropy, this x log 1 over x, with a different function, x to the alpha, for some alpha in 0, 1. And if you do this, you really recover these, the recourse bounds that I promised you. So this should look more familiar. And it turns out the entropy connection was very useful for us. This quantity that I wrote is known as Salas entropy, and it's a parameterized generalization of Shannon entropy. This is really like sort of a shifted and scaled version of Salas entropy. But the limit of the original Salas entropy as alpha goes to 1 is the Shannon entropy from before.
To clarify, we're just changing the analysis. We're not changing the algorithm.
Absolutely. So the algorithm knows nothing about this potential function. It's completely oblivious to the potential. This is just an analysis tool. So, the algorithm is just what I showed you. It's like, do swaps and do gamma moves until you can't do any anymore. You're playing cleanup with your solution.
So let me understand, for the original, sorry, go ahead.
Oh, sorry. And we don't, you can do these in arbitrary order. Like,
yes.
It's just look around by some arbitrary method, find one of these, do it, repeat until you can't do anymore.
Exactly.
Okay.
Now, you can always do this in polynomial time, but that's sort of
sure.
like not relevant for the bounds that I'm claiming. Yeah.
So does the big O of Gn, does it hide a constant depending on alpha?
It does, yeah.
Okay.
But yeah, we'll also set alpha to be, for this talk, you can think of alpha as 1/2. I was going to do it at the end, but yeah.
Thanks.
Right, quick question. So the pi i's here, these are our choices or ordering for the current things that we select, right? So
right, yeah.
So this entropy really is just like the entropy of this histogram that you drew.
Exactly.
I see.
Yeah. So in Salas entropy, like the true Salas entropy, like you're shifting and scaling such that at 1, this thing is like the limit is not defined, but yeah.
So what's going on is really what you're doing is you're looking at the entropy of this distribution, and you're bounding how the entropy can change after a given insertion or deletion to the constraints. And there's a natural bound of f max just because that's how much a constraint can change.
Exactly.
That's a natural bound of like upper bounding any individual point in the distribution, but it's probably a little bit more non-trivial to show that the entropy overall changes because you can imagine it like contributing a little bit to everything or something like that.
That's true. It turns out to not be too much harder. It's basically what you said, plus the fact that this function is concave. But yes, yeah. We'll say this sort of explicitly. So let me try. I can hopefully give you this entire proof. I'll try my best. The workhorse essentially the main things we're using is that this function x to the alpha is non-negative, monotone, and concave. Here's the graph of x to the alpha when alpha is 1/2. For our purposes, we can just think of this. And I've put the potential function here just to remind you what it is. Okay, claim 1, phi alpha is non-zero. This part should be easy. As in, okay, non-negative, fine. All right, claim 2, phi alpha does not increase with swaps. So suppose I do a swap. I move blue ahead of red. Oh, sorry, oh, did I put these in the wrong direction? No, this is fine, sorry, good. Confusing myself. So suppose we did a swap. Well, we know that red might get taller and blue might get shorter, but never the other way around. And so really, the fact that x to the alpha is concave already means that we're done here. So why is this? The total coverage in the system is staying constant, and only these two bars are changing. So the red bar is increasing by some amount k, and the blue bar is decreasing by the same amount k. So the fact that x to the alpha is concave means that 1 unit of movement in this part of the graph makes for smaller change in the y-axis than 1 unit of movement in this part of the graph. So, the blue bar is decreasing like out here, and the red bar is increasing up here. But so the blue bar is going to contribute a bigger decrease to the total potential. That's it. Did that make sense?
Is it obvious that the decrease in the blue or the increase in the blue is the same as the decrease in the red?
Yeah, so the coverage vector is just defined as like the value given what came before. So anyone proceeding in the permutation, nothing's changed from their myopic point of view. Anyone following in the permutation, also nothing's changed from their myopic point of view. They're still conditioning on the same prefix, just in a different order. So only these two can change. And the total coverage is always the same. This is sort of like at a fixed time step. We're not changing the functions up like during this sort of swap.
So it's important that red is bigger than blue at this point, because
Yes.
what this is kind of saying is that the entropy is only decreasing because things are becoming closer to singular. But if red was smaller than blue, they could become closer to the uniform, which would be the
Exactly.
To clarify something, I think you said that red would go up by the same amount that blue goes down, but I think what you meant was, blue could go down more than red goes up, couldn't it?
No, so that's what I just said to Danny.
You're saying the sum over all the elements has to remain constant in the two cases?
Yeah, so this is sort of at a fixed time step. The world is not changing. We have the same constraints as, across this.
Because these both achieve that same Fn.
They both achieve the same Fn, exactly.
Okay, and it's just who's responsible for what that's changed.
Exactly, we're kind of reassigning responsibility, exactly. Okay, so the third thing to argue is that this potential increases by a bounded amount when the constraint g arrives. And this is almost what Raj said. So when a function g arrives, we're sort of adding some coverage contribution to some of the elements. And again, since x to the alpha is concave, this increase is the worst when this when it's sort of spread out across as many people as possible. Now recall in this talk, we assumed that this function was integer valued. And so each of these sort of shaded regions has height at least 1. And by concavity, kind of the impact is biggest, at this part of the curve. And so the worst case is when we take our g of n, cut it up into pieces of size 1, and give them to kind of empty coordinates. That's the worst possible case. And okay, square root of 1 is 1, so this max increase in the entire potential is still g of n at most. All right, let me try to get through this last piece, and this is the most interesting part. So now the final thing we need to show is that we spend enough energy when we do a gamma move. So suppose u jumps ahead in line, as before. And recall, jumping ahead in line is the gamma move if it's gamma times taller than anyone it cut in line. Let's define these two quantities, vi and ai. So by vi, I just mean the marginal contribution of the ith person, sort of in this picture. So this is like VI. And AI is the change to this marginal contribution after I also condition on U. So really, AI is just the amount that U is stealing from these people. All right, that's just notation to make the analysis a little bit cleaner. We're trying to measure the potential change. So it's the potential after minus the potential before, which is this expression. Okay, what are all of these terms? This is the contribution of U after. So suppose for simplicity just that U, which is U is the person jumping, was initially empty. So U's initial height was 0. Then U's height after is exactly the amount that U stole from everybody. So it's just the sum over I of AI. And so U's contribution to the potential is this term to the alpha. Now each person that U cut in line after the move has a height of VI minus AI. And so it's contributing that to the alpha. And before the move, it had a height of VI. So it's contributing just VI to the alpha. So we're almost done. Let's just power through this quickly. Sorry, erase this. Okay, so you'll notice the second term here, we can bound just with the first order Taylor approximation. So this is kind of like, we're moving from VI to VI minus AI. So we're moving in each coordinate by AI. And we want to know what is the change in the y-axis when we do this move. Well, concavity means we can bound this decrease in the height by the first order approximation. So we draw the first order approximation at VI, and this is an upper bound on how much we'll move in the y direction. So, okay, if this is, yeah, I hope this is not too fast, but I mean, this is the derivative of x to the alpha. And so if you thought about this for a moment, you wrote this down, this is the first order approximation. And we know that the change in potential needs to be bounded by this. So this looks like we might have taken a step in the wrong direction, because how do we compare these terms? Really, we want to show that this change in potential is at least -1, right? And I've kind of introduced like AI times VI. This seems somewhat nasty. But it's not too bad, because recall this moving U was a gamma move. And what is the definition of a gamma move? It means that U's height after the move is gamma times anyone's height before the move. U's height is the sum over I of AI, as we argued. Vj is the height of any person J that was in between before the move. And so a gamma move means sum over I of AI is larger than gamma times Vj. Okay, so there's a negative sign here. Alpha is between 0 and 1, so this exponent is negative. 2 wrongs make a right, and we can reuse this inequality in the right direction and essentially bound this VI term by sum over I of AI to the alpha -1 divided by gamma to the alpha -1. And rearranging it gives this. And this kind of magically has the same AI terms, sum over I AI to the alpha. From here, it's just a matter of setting parameters. If you set alpha to be 1/2 and gamma to be 16, this term is actually a constant, it's just 2. 1 minus 2 is -1. And the last thing you need is that the sum, this function was integer valued, and so the sum over I of AI, this is just the height of U, is an integer. And it's non-zero. And that's the entire proof. Any questions about this? I know this is maybe a little fast, but. Okay, so I'll just say very quickly, like this was the proof for the unit cost case. To generalize, you need to do a few things. So if you want to run the greedy algorithm, you need to maximize not just the sort of marginal coverage of each element, but the bang for buck of each element, i.e. the marginal coverage divided by its cost. And this makes you need to do a few things. You need to replace the potential function with a more complicated potential, and then actually set the parameter alpha carefully. But I don't really have time to talk about this. So the takeaway here is that there is a way to generalize. It's a little bit more complicated. And it loses this extra log C max over C min factor in the recourse. That's it. So I don't think I have too much time to talk about this. Maybe catch me later and I'll describe to you what 3 increasing functions are. I'll just say, so in our paper, we give some applications of this framework to problems besides submodular cover. So we can actually show an algorithm for the dynamic Steiner tree problem in this low recourse setting. So we can get order 1 competitive ratio guarantees with average recourse log of the aspect ratio of the metric, whatever that is. Again, catch me later and I can tell you what this is. And this is not the best known bound. So Anupam and Amit Kumar showed a better bound, but our proof is especially simple. And I find it exciting and promising that maybe you can use this framework for other things. So that's it. Let me just conclude. So takeaways from this talk: we simplify previous work on dynamic low recourse covering problems. We generalize to a significantly wider range of problems than was previously known. We introduce a new potential function, Salas entropy, in this dynamic algorithms context that we hope finds uses elsewhere. There's a bunch of open questions remaining from this work. One immediate thing is, can you remove this log Cmax over Cmin term? I don't know if it's inherent to the analysis. I don't know if it's inherent to the algorithm or if it's inherent to the problem. But I would love an answer if you want to help me answer it. Raj, you asked if you can give worst case bounds. I don't know. It's an interesting question. So the recourse bounds we gave are fundamentally amortized. The potential function method is kind of fundamentally an amortized technique. And I don't know if you can bound the worst case recourse. Can you use this local search framework or the potential function for other problems in dynamic algorithms? What about an update time variant of this problem? You know, what if I care about computation time as opposed to the recourse? I also don't know. Okay, and finally, can you characterize this class of 3 increasing functions? This would have made more sense maybe if I told you what that is, but yeah, that's another question. So I'm a little bit out of time. Thank you very much for listening. And I will take any questions at this point.
So I wanted to maybe re-ask a question I asked earlier, but more articulately expressed. So I guess like your problem is like I give you this hard submodular constraint where this submodular constraint is like some linear combination of submodular functions, and I say you have to maximize it. And I give you like sort of an objective which is linear, and I'm basically allowing you a little bit of wiggle room in your linear objective, but like your submodular constraint is hard, like you have to always maximize it. Mm-hmm. And now if I flip these and I say always, let's say I give you like a hard linear constraint, so like by at most blah many elements in vertex cover or something, but I give you as your objective a submodular function, which is maybe still evolving over time, then I guess I'm wondering if this stuff applies. And it seems like, you know, set cover is to your problem as maximum coverage would be to this problem.
Right.
And, yeah.
Yeah. So people study exactly what you're saying, like dynamic versions of, maybe people call this like submodular optimization subject to block constraints, you know, cardinality constraints, knapsack constraints. And I think there is no like work on dynamic variants of this, of your version of the problem. Even with like recourse guarantees, yeah. Okay,
cool. Okay, I mean, I guess I figured that like probably your stuff would also immediately give results for this, but I don't know.
Yeah, I don't think so, but yeah, I guess it depends what your model is exactly for what's changing, and like the issue could be that like the solution that's being induced is not as nice as the one that I'm using. But maybe I should think about it before I answer that.
Okay, yeah, thanks.
Yeah.
A quick question, Roy.
Mm-hmm.
So this is a modeling question. This different notion of recourse versus objective trade-off. Aren't some variants of these types of allocation problems where, you know, opening a facility has its own cost? So it's in some ways as if recourse is part of your objective. Does that make sense?
Yeah. So you're asking about facility location version, like a facility location.
This recourse cost is part of your objective function rather than two different things, an objective function and a different trade-off with recourse.
Yeah. So I'm trying to think of examples of this. So there's So I know Anupam has this paper that models some kind of I'm actually forgetting exactly what it was, but for a class of problems, like you want to minimize like the sum of like the objective at that time plus some like movement cost. This iCalp paper, I'm forgetting the name of it, but people have studied sort of like adjacent problems, but they're not exactly the same as this problem. Does that answer your question?
Okay, yes. So they will be very different problems, right? Techniques wise.
No, changing bases, multi-stage optimization. Yeah, I can show you this, or send you this paper if you're interested. But yeah, it's sort of a different objective.
Okay. Thanks.
Of course, like you can really generalize this in like all kinds of ways. You can say like, what if a recourse is non-uniform? You know, you can, yeah. But this is the problem that we consider.
Yeah, thanks.
Any more questions?
Actually, quick question. So suppose that you had this analysis for this potential function, like the entropy or the Salas entropy. Does this analysis tighten at all if you're only given insertions, if you're in the insertion only world, as in the first paper you had? So you're allowed to make some changes now, but you only have insertions.
Yeah, so to be honest, okay, so maybe I forgot to even say this. We didn't really even talk about what happens in deletions. And all our potential function is saying, like, the only thing I need to claim is that deletions actually like don't increase the potential. And they don't because the function is monotone. So when I delete stuff, like I'm just like losing some, you know, some height from some of these vertical bars. And because the potential is monotone, we're only losing potential. So we're kind of like ignoring the deletes completely. I mean, this is not answering your question. Like, I don't know if you can do better with an insertion only version. But actually, so, I mean, you won't be able to do much better. Like at most, you'd be able to sort of shave this log factor.
Right, because you're bounded by the green.
Yeah, and I don't know how to do that.
Actually, I'll ask a quick question as well. So you talk about this Salas entropy. It looks a lot like something I remember called Rainey entropy, which is also often parameterized by alpha. I don't, to be honest, I don't even remember the precise definition of Rainey entropy, but are they similar or? Yeah,
no, so they're not exactly. I also don't remember the definition of Rainey entropy, but I do know that when I was, when we were doing this, we were like, oh, we were kind of surprised that this, you know, entropy even worked in the first place. And so we, you know, we threw the kitchen sink at it, and we tried Rainey entropy, and I don't recall, or in fact, we couldn't get anything to work with Rainey entropy, and so it's not the same as Salas entropy is the short answer. So this proof, like the end of this proof is sort of like weird. It requires some sort of some slightly strange properties. You know, terms need to sort of cancel out in exactly the right way here. And it magically works for Salas entropy and for Shannon entropy. I don't remember if I could even get this part to work for Rainey entropy.
I think this is also, I mean, this entropy thing, isn't it sort of similar just to like some sort of P norm, but like you raise it to the power P kind of, but it's just like P less than. Yeah, I don't know if that's a useful viewpoint on it, but
yeah, absolutely. So you can call this whatever you want, you know, like
yeah, of
we
course.
call it entropy.
Yeah.
just because the entropy viewpoint was sort of useful in coming up with this.
It's
really just, sums of things to the power of something less than 1. It's not a norm because this is less than 1, but whatever, quasi-norm or whatever people call these things.
Yeah, of course.
Concavity seems to be like kind of the big workhorse here. Yeah.
So the Rényi entropy really is log of a LP norm, right? Times some scaling factor that depends on that P norm, and then when you send P to 1, that becomes the entropy.
I see.
So I think another viewpoint is like log of the P norm of the vector times some constant.
Cool. Any more questions?
I guess I have a question. You mentioned that you don't change your solution at all on deletes. Is there a reason to believe that that's not a useful capability to have?
Oh, sorry. I didn't mean that we're not changing our solution.
Is it just
we're not, the analysis is not even thinking about this as a benefit. You delete some stuff and your solution might become unstable. So you might need to do some new local moves.
Okay.
But I guess all we really need to say is that energy is not entering the system when you delete a function. And so it might cause you to do some stuff, but you're most going to use the energy that you already had in the system.
Oh, okay. So we've sort of pre-charged for all those changes.
Exactly. Yeah.
Okay. Thanks. All right. Well, we are a bit over time, so let's thank our speaker.
Thank you, everybody, for coming.